In the previous lecture, we started proving Kummer theory for cyclic extensions. Kummer theory briefly mentions, Kummer theory gives us a natural bijection between group homomorphisms from automorphisms of f bar over f to cyclic group of order n, and group homomorphisms between f cross to cyclic groups of order n. So this is the cyclic part of Kummer theory, and we can also interpret it as having an internal description of all the cyclic extensions of field F that can be embedded into Z sub n, assuming that F has all the nth roots of unity, meaning it has at least one element of order n. From there, we can deduce that it has all the elements of order n inside the base field F. So let's go through the statements and see what is the exact formulation of the result. So we start with a field that has characteristic 0, and we denote one of its algebraic closures by f bar. As I mentioned, we assume that f has an element of order n, and let's call it zeta. The group generated by zeta we are going to denote by m sub n. So m sub n is a cyclic group that has n elements. The elements are 1, zeta, zeta squared to the dot, zeta to power n minus 1. Now, on one hand, we have this external object, which is the set of all the extensions of f that are Galois, and the Galois group of E over f can be embedded into the cyclic group of order n, a cyclic group of order n, Z sub n, let's say. On the other hand, we have this internal object, the set of all the cyclic subgroups of f cross over f cross to the n. Notice that if I give you a group homomorphism from f cross to Z sub n, then all the elements raised to power n would be in the kernel of such group homomorphism, and therefore such a group homomorphism factors through f cross over f cross to the n. And because the image of such group homomorphism is a subset of the cyclic group Z sub n, it is cyclic as well. So you can see that there is a bijection between group homomorphisms from f cross to a cyclic group of order n and cyclic subgroups of f cross over f cross to the n. So this part we can interpret as an internal set of objects. Now we want to give a bijection between these two sets. We start by defining lambda that takes a cyclic subgroup of f cross over f cross to the n and spells out a cyclic extension of the base field f that where the degree extension is a divisor of n. So what is lambda? Lambda of the cyclic group generated by the coset that's represented by A is nothing but the field generated by f and nth root of A. And this symbol nth root of A is nothing but a 0 of x to the n minus A in the algebraic closure that we have chosen. There are, of course, certain ambiguities in this equation. So one of them is that we can choose different zeros. The other one is we can choose different generators for this cyclic group, or we can choose different representatives in order to denote this generator. And we have discussed in the previous lecture why lambda is well defined, why all these choices do not matter, and at the end we end up getting the same field, and why the field that we are getting is indeed in the codomain. So these are the issues that we have to address when we say lambda is a function from this set to the other one. And this is what we did in the previous lecture. I'm going to go over some of these items in the proof as well, but we have essentially proved well-definedness of lambda and delta in the previous lecture. Now, what is delta? Suppose E over F is a Galois extension and it is cyclic, and the degree of this extension divides n. Alternatively, I can say that the group of automorphisms of E over F can be embedded into a cyclic group of order n. Then delta of E is defined to be all the elements of E that we can raise to power n and get a unit inside F. So we take this set, that would be a subgroup of E cross, and that would be a subgroup of F cross, and then we mod it out by F cross to the n. So of course, delta of E would be a subgroup of F cross over F cross to the n. What is not clear is why this subgroup is cyclic. This is another result that we proved in the previous lecture, that delta is a well-defined map, and that means here that delta of E is indeed in the codomain, which means it is a cyclic subgroup of F cross over F cross to the n. Now, what we want to show in today's lecture is that this lambda and delta are inverse of each other. And moreover, the Galois group of E over F is isomorphic to the group delta of E. So we get a complete understanding of the Galois group of such field extensions. This isomorphism, so to speak, is not a natural isomorphism, but we will see how the proof goes. Essentially, the way that we are going to show this isomorphism is by arguing that both of them are cyclic groups and they have the same cardinality, and from there we deduce that these groups are isomorphic. An alternative way of formulating more or less the same result is saying that the automorphisms of the field extension F joined with nth root of A is isomorphic to the cyclic group generated by the coset represented by A in F cross over F cross to the n. Generated. So the main tool for us to prove delta and lambda are well defined and get the rest of the argument is a function that is called the Kumar pairing of the groups of automorphisms of E over F and delta of E. We defined the Kumar pairing, and let me quickly recall what it is. So suppose that I give you an element of automorphisms, F automorphisms of E, and I give you an element inside delta of E. Let's call them sigma, and an element of delta of E, remember, it looks like some element of E raised to power n that happens to be inside F, the coset that's represented by that element. So suppose that element is alpha. So I'm getting alpha raised to power n. The assumption is that alpha raised to power n is in F cross, alpha is inside E, and then I'm looking at the coset that alpha to the n represents in F cross over F cross to the n. I give you such a coset and I give you sigma. Then what does the Kumar pairing give us? It applies sigma to alpha and divides by alpha. Of course, again, there are many issues here. For instance, I have to say why this value only depends on the coset that's represented by alpha to the n. Here it means that what happens if I choose different alphas that give me the same coset? Do I end up getting the same quantity, the same value on the other side? The other issue that I have to address is why sigma alpha over alpha belongs to the codomain, which means why is it a power of zeta? Again, we have addressed these issues in the previous lecture, and we showed that the Kumar pairing f is indeed a well-defined function. Moreover, we proved that if I focus on one component at a time, so let's say I fix the second component and allow sigma to change, then I end up getting a group homomorphism on sigma. If I fix sigma and allow an element of delta E to change, I just allow the second component to change, again, we end up getting a group homomorphism. So that's part of saying that it's a pairing. A pairing of two abelian groups is such a function, where the codomain in general should be inside S1, the group of complex numbers that have norm 1. Okay, so let's again introduce the needed notation. So I often put bar on an element inside F, and then from there, by using this bar, I'm denoting the coset that this element represents in F cross over F cross to the n. So alpha to the n bar means the coset that's represented by alpha to the n, which is essentially this one. Now, if I fix this one, I can view F as a function over only the first components to the codomain, and that means that I'm getting a function from F automorphisms of E to the cyclic group of order n m sub n that's generated by zeta. So essentially, f of alpha bar to the n, f sub alpha bar to the n of sigma is f of sigma comma alpha to the n. Similarly, I can define f sub sigma. This time I'm fixing sigma and allowing elements in delta of E change, so I get a function from delta of E to m sub n, which is the cyclic group generated by zeta. So again, fixing sigma, given alpha bar to the n, maybe it's better to put a power n over here to become compatible with the previous notation. So we end up getting group homomorphisms. Again, these are the results that we proved in the previous lecture. So both f sub alpha to the n bar and f sub sigma are group homomorphisms. Now let's go to the proof and see where we are. Again, as I mentioned, we have proved that delta is well defined. That means, as part of that, we need to address this issue that if I give you two generators of the same cyclic group, so let's say the coset represented by A1 and the coset represented by A2, both of them generate the same cyclic group, then A sub 2, being a coset representative here, should be a coset representative of one of the elements on the other side. That means A sub 2 should be A sub 1 raised to some power times this some element inside this subgroup, which means C to the n, for some C inside F cross. Now, when I take nth root of these elements, this means when I take a solution of x to the n minus A sub 2, I end up getting, so then nth root of this is one such solution. Nth root of A sub 1 to the I times C is another such solution. And because all the solutions differ by a multiple of power of zeta, I deduce that nth root of A2 is some power of zeta times C times nth root of A1 raised to power I. In particular, I can deduce that the field generated by the nth root of A2 joined with the base field F is contained in the field generated by the nth root of A1. Now, I have symmetry between A1 and A2, so I can flip the order of this inclusion and deduce that they are indeed equal. So altogether, we get that this function lambda that assigns to the cyclic group generated by the coset represented by A, the field that's generated by the nth root of A together with the base field is a well-defined function. Now, let me also quickly recall how we showed f sub sigma is a well-defined function. We argued that f sub sigma naught, the group homomorphism that we got out of the Kumar pairing from delta of E to m sub n, is indeed injective. The way that you can argue, okay, so you pick some coset in the kernel, and that means alpha to the n, alpha bar to the n is in the kernel, and this quantity is nothing but sigma of alpha over alpha. So sigma of alpha over alpha is supposed to be 1. That means alpha belongs to the fixed point of sigma. Now here we are assuming that sigma naught, or sigma that I said, generates the entire Galois group of this extension. So being in the fixed points of sigma naught implies that it is in the base field capital F. So this alpha should belong to the base field capital F, which means alpha to the n belongs to the F cross to the n, and therefore the coset that we are getting is just 1. So this is how we showed F sub sigma naught is injective. Now, F sub sigma naught being an injective group homomorphism implies that delta of E can be embedded into a cyclic group of order n, and therefore delta of E itself is a cyclic group. And that shows that delta is well defined. Now we want to show lambda O delta is identity. Now let's spell out what it means. Delta takes delta of E, so I have to take an intermediate subfield and then give it a group, and then I have to, so actually I'm first addressing the other way around. I want to take a subgroup, and then this cyclic subgroup I assigned an intermediate subfield, and then I apply delta in order to get a subgroup. So we want to show that delta O lambda is identity. When I apply lambda to the cyclic group generated by the coset represented by A, I end up getting this field. When I apply delta to this field, I have to raise it to power n, intersect it with the base field, and then look at the quotient of this group by F cross. We want to show that this equality holds. So as always, whenever you want to show equality of two sets, you need to argue that one set contains the other one, the other side, and vice versa. One of the inclusions is immediate from the definition. So notice that the nth root of A raised to power n is A, which is inside F cross. This means that this element A belongs to this intersection because I am raising this guy to power n and I am getting some elements inside F. So A does belong to the numerator, which means the coset that's represented by A is in the left-hand side in this group. And therefore, the cyclic subgroup generated by this element is a subgroup of the left-hand side, which means left-hand side contains the right-hand side as a subgroup. Now I want to show the other way around. I'm going to pick an element inside the left-hand side, and I want to show that it belongs to the right-hand side. An element of the left-hand side, how does it look like? It's a coset represented by beta to the n, where beta is inside E, beta to the n is inside F. Let's call beta to the n to be small b. That's an element of the field F. And for simplicity, let's denote beta to be the nth root of this small b. After all, beta is a 0 of x to the n minus b. And I can choose the notation, the nth root of b, to denote this particular beta that we started with. Then I want to argue that the coset that's represented by b in f cross over f cross to the n belongs to the cyclic group generated by the coset that's represented by a. That's my goal. Okay, but what do I know about this element b? I do know that it belongs to both. Okay, what do I know about this element beta? I do know that this element beta belongs to E, and that implies that the field generated by the base field and beta is an intermediate subfield of the extension f joined with nth root of a over the base field f. So this is an intermediate subfield. But remember, the group of automorphisms of the original extension is a cyclic group. And therefore, every subgroup is a normal subgroup. From there, we can deduce that every intermediate subfield is a Galois extension. And moreover, the group of automorphisms of every intermediate subfield would be a quotient of the group of automorphisms of f joined with nth root of a over f. And therefore, all the intermediate subfields have cyclic Galois extensions. Now, our cyclic Galois extensions have cyclic Galois groups. So this is exactly what we have argued, that this surjects onto the group of automorphisms, f automorphisms of f joined with nth root of b. This is a surjective map. In particular, when I start with sigma naught, generator of this group of automorphisms, when I restrict sigma naught to this intermediate subfield, I end up getting a generator of this cyclic group. Now I can work with the Kumar pairing of not the original field extension, but rather this field extension that we have over here. So this Kumar pairing, I use this B bar, and so this gives me a group homomorphism from the group of automorphisms of this field extension to the nth root of unity. And I can do the same for the original one. And we have discussed that these group homomorphisms are injective. So let me quickly recall how the proof goes. If I give you an element over here that's in the kernel of this map, that means that sigma applied to the nth root of b spells out the nth root of b back. That means that nth root of b is fixed under sigma, f is fixed under sigma, so sigma is identity. This is how we showed this is injective. Similarly, this is injective. So we are getting two subgroups of m sub n, and because this is a quotient of this one, the cardinality of this group divides the cardinality of this group. Similarly, because f sub a and f sub b are injective maps, we get that the cardinality of image of f sub b bar divides the cardinality of image of f sub a bar. F sub a bar and f sub b bar, both of them are injective maps, so the image has the same cardinality as these guys, and that's why we can argue that this cardinality divides the other one. At the same time, they are subgroups of the cyclic group M sub n. So these guys are subgroups of the cyclic group M sub n, and their cardinality divides each other. From there, we can deduce that image of f sub b bar is a subgroup of image of f sub a bar, because we know that the lattice of subgroups of cyclic groups is the same as the lattice of divisors of n with respect to divisibility. So knowing that the cardinality of image of f sub b divides cardinality of image of f sub a bar, we can deduce that image of f sub b bar is a subgroup of the image of f sub a bar. You see the crucial way that we have been using the Kumar pairing in this argument. Now, what is image of f sub b bar and what is image of f sub a bar? Recall that again, f sub a bar is such a group homomorphism from this group to m sub n, and this group is a cyclic group that's generated by sigma naught. Therefore, the image of this group homomorphism is generated by f sub a bar sigma naught. And what is f sub a bar sigma naught? This is nothing but sigma naught over the nth root of a over the nth root of a. Now, similarly, f sub b bar applied to this group gives us the image. This group is cyclic and is generated by sigma naught restricted to this intermediate subfield. Now, when I want to understand the image, I have to apply fb bar to this generator. And that means I have to apply fb bar to sigma naught restricted to this intermediate subfield. And again, the way that we defined f sub b bar, this means I need to apply sigma naught restricted to this intermediate subfield to nth root of b and then divide out by the nth root of b. So this particular nth root of unity belongs to the image of f sub a bar, and f sub a bar is generated by this element, and this element is sigma naught of nth root of a divided by nth root of a. So altogether, we get that this fraction, this ratio, equals to this 1 raised to power I for some power I, because that's the group generated. Every element in the cyclic group generated by this element is this 1 raised to power I for some integer I. Now, what we can do from here, I can put the sigma naughts on one side and the constants on the other side, and through that we get that sigma naught applied to the fraction nth root of b divided by nth root of a raised to power I is the same as the same fraction, which means this fraction belongs to the fixed points of sigma naught. But fixed points of sigma naught, so the group generated by sigma naught is the entire group of f automorphisms of E, and E over F is a Galois extension. And therefore, the fix of the group generated by sigma naught is the base field, capital F, which means that this fraction is an element inside capital F. So again, let's go over this argument. This belongs to the fix generated by a fix of the subgroup generated by sigma naught, but that group is the entire automorphisms of E over F. And therefore, because this extension is Galois, the fixed points of this group of automorphisms is the base field. From there, we deduce that the the numerator is just the denominator times something inside the base field, capital F. So the nth root of b is nth root of a raised to power some integer times some element of f cross. If I raise both sides to power n, I deduce that b is a to power I times c to the n. That means the coset represented by b, which is b bar, is the same as the coset represented by a to the I, and this guy disappears because this belongs to f cross to the n. So the coset represented by b, which is b bar, is the coset represented by a to the I in this quotient. So in particular, b bar belongs to the cyclic group generated by a bar. And that's exactly what we wanted to show. That's how we started this whole setting. So we deduce that this b bar, which is beta to the n, the coset represented by beta to the n, is an element inside the cyclic group. This was an arbitrary element of delta of E. From there, we deduce that delta of E is a subgroup of the cyclic group, which shows equality of these sets. So from here, we conclude that delta of this in this field is a subgroup of the cyclic group. From there, we deduce that this equality holds, which means delta O lambda is identity. Okay, so next we want to show that lambda O delta is also identity. What does that mean? I'll start with some intermediate subfield, which is Galois over F, and the group of automorphisms is cyclic, and it can be embedded into Z sub n, cyclic group of order n. Now, one of the crucial results is what we have already discussed when we were proving Galois solvability criterion, solvability result. We proved that if F has an element of order n, then every extension, every Galois extension that is cyclic and the cardinality of the group of automorphisms divides n is a Kummer extension. So what does Kummer extension mean? It means that E is generated by F and nth root of A for some A inside F cross. How did we prove this? We used Hilbert's theorem 90. We said that if zeta is an element of order n, then when I take norm of zeta, I end up getting 1. From there, we used Hilbert's theorem 90 and deduce that zeta itself is sigma of beta over beta, where sigma is a generator of the group of the Galois group of this extension. Now, looking at this sigma of beta, we deduce that this beta has precisely, I mean, the orbit of this beta has precisely the degree of the field extension number of elements. From there, we deduce that, and when we apply sigma to the i's, we get that they are zeta to the I times beta, so we get different elements inside this orbit, and all of them should be zeros of the minimal polynomial. From there, we deduce that the minimal polynomial looks like x minus beta times x minus zeta beta, and so on. From there, we deduce that beta to the n is an element of the base field, and this is how we proved that such an extension is always a Kummer extension. So we used Hilbert's theorem 90 to show that if my base field has enough roots of unity, and my extension is cyclic, it's a Kummer extension, which means that E is F joined with nth root of A. Okay, this is what we had earlier. What does that mean? This means, and this field extension is in the image of lambda. Essentially, what we have argued right now is that lambda is a surjective map. So everything is in the image. You see, now this together with the previous result immediately give us the other way around. So let's think about it a bit before I continue. So I have the set of, so what did we prove so far? We have this delta O lambda is identity. So I have this set, and then I have lambda, and then I have this set, and I have delta, and I go back, and we show that this composite is in fact identity. So whenever you have such a statement that delta O lambda is identity, you can immediately deduce that lambda and delta induce bijections between image of lambda and the domain. So this via lambda goes to some copy of this domain inside the codomain, and then delta sends that guy back to where we started. Now, when I tell you that delta is surjective, this means that this copy is in fact the entire codomain. From there, we can deduce that delta and lambda are inverse of each other. So essentially what I'm saying is that knowing that every cyclic extension of degree dividing n is a Kummer extension immediately, together with the fact that delta O lambda is identity, immediately implies that lambda O delta is also identity. But let's go through the argument. So delta of E is delta O lambda of the cyclic group, because E is lambda of the cyclic group, but delta O lambda is identity, so I get back the cyclic group. And the cyclic group, so now I can apply lambda to both sides. I get that lambda O delta of E is lambda of the cyclic group, which is E, because of this. As we can see, this is quite general at this stage. So we get that lambda O delta is also identity. At the final step, I want to point out that the group of automorphisms of this field extension is isomorphic to delta of E, as soon as E belongs to this. E over F is a cyclic extension, and the degree of the extension divides. So suppose that this side is generated by sigma naught. I know the other side is also cyclic, so suppose that the other side is generated by the coset that's represented by A naught. Then I have two embeddings using Kummer pairing. I can fix sigma naught and think about the Kummer pairing just as a function in terms of the second component. So I get this embedding, and we prove that in this case it would be an embedding. So we get an injective group homomorphism from delta of E to M sub n. Similarly, I can do the same, but this time I'm going to fix the second component, and I'm going to fix it to be this A naught, the coset that's represented by A naught. Then I get an injective, again, we prove that it's going to be injective, an injective group homomorphism from the Galois group of E over F to the cyclic group just generated by Z. Now, this cyclic group is generated by A naught bar, and this cyclic group is generated by sigma naught. So the image of F of sigma naught is generated by F, the Kummer pairing of the pair sigma naught and A naught bar. Similarly, when I look at this one, the image of this one is generated by when I apply this group homomorphism to a generator of the domain, which means when I apply it to sigma naught, for instance, I get a generator of the image. So when I apply this guy to sigma naught, I get the same Kumar pairing by definition. So this means that image of f sub sigma naught is the same as image of f sub a naught bar. So these are the same groups, the same subgroups of m sub n. And both of these group homomorphisms are injective. So the domain of the first one is isomorphic to this image, and the domain of the second one is also isomorphic to this image. So altogether, we deduce that delta of E is isomorphic to the group of automorphisms of this extension. As you can see, the argument is not providing a natural isomorphism between these two groups, but rather showing that there exists some isomorphism between these groups. We show that both of them are cyclic groups of the same order, so that's why they are isomorphic. Now again, the rest can be done just using language of sets, but nevertheless, let's go over it. So the automorphisms of this extension by the part that we have already proved over here, and the fact that, okay, so by this fact that the group of automorphisms of such a field extension is isomorphic to delta of E, we know that this other group of automorphisms is isomorphic to delta of this field. But this field itself is lambda of the cyclic group. So it is delta O lambda of the cyclic group, but delta O lambda is identity. So it is the cyclic group that that's generated by the coset represented by A, and that's exactly what we wanted to show. So this is isomorphic to the cyclic. So altogether, now we are done with the proof of Kummer theory for the cyclic case. Now let's go beyond that. So the Kummer theory, we are going to discuss only the finite case of it, but it is true for abelian groups. So alternatively, I can say, so the way that I interpreted the previous statement was using group homomorphisms from automorphisms of f bar over f to cyclic group of order n, and group homomorphisms from f cross to cyclic group of order n. I can replace cyclic groups of order n by z sub n cross z sub n cross z sub n, finitely many of them. For both of these sides, I can consider group homomorphisms from automorphisms of f bar of f automorphisms of f bar to finite copies of z sub n, and I can do the same for group homomorphisms from f cross. And what Kummer told us is that there is a bijection between these two sets, similar to the cyclic case. Alternatively, I can formulate it like this. Again, the assumptions are the same as before, that f is of characteristic 0. It has an element of order n. F bar is an algebraic closure of the base field f. This time, the set of intermediate subfields that I'm interested in consists of those, I'm going to denote it by this, A, B stands for abelian, N stands for n torsion of exponent n. This means that every element raised to power n is identity. Now, we are interested on the intermediate subfields where the Galois group of the extension is Galois, and the Galois group of extension is finite, abelian, and it has exponent n. So here again, I need to emphasize that it is E over F is Galois. So it's a Galois extension. And the extension is a finite Galois extension. And the Galois group is an abelian group, and it is of exponent n. Again, exponent n means every element inside this group raised to power n is identity. So that means that it is of exponent n. On the other side, I'm interested on all the finite subgroups of f cross over f cross to the n. Again, I'm interested on group homomorphisms from f cross to a finite abelian group that's n torsion, and that means that it factors through f cross to the n. So this means that I'm interested in every finite subgroup of f cross over f cross to the n. So it comes, so on one hand, I'm working with finite Galois abelian extensions of exponent n. On the other hand, I am working with finite subgroups of f cross over f cross to the n. So again, alternatively, I'm working with finite abelian quotients of automorphisms of f bar over f that have exponent n, and finite abelian quotients of f cross that have exponent n. Now, there is a bijection between these two sets. What is the bijection? Lambda of a subgroup. I'm going to take elements of this subgroup. Elements of the subgroup are cosets that are represented by a sub i's, where a sub i's belong to the field capital F. For each one of these a sub i's, I'm going to pick a solution of x to the n minus a sub I inside the algebraic closure that we have and add it to the base field. So I'm adding finitely many zeros to the base field F, and this way I'm getting an intermediate subfield. That's lambda. Now, what is delta? Delta of an intermediate subfield is the same as before. I look at that elements of those elements of the subfield raised to power n that happen to be in the base field. And then I look at the cosets that those elements represent. So it's similar to the previous case. Delta is identical to the previous case. Lambda is different here because there the groups were cyclic, so we had only one generator, and that was enough to add to the base field. Here I'm looking at all the elements of a bar, and then I'm looking at the nth roots of that element and add them to the base field. So a priori, it's not clear. I mean, it's not clear why this lambda is the same as the lambda that we had before if a bar is cyclic, but it is the case because we proved Kummer extension for the cyclic case. We can deduce that this lambda is consistent with the lambda that we had earlier for cyclic extensions, even though a priori we are adding more elements to the base field in this way. So the claim is that lambda and delta, both of them, are inverse of each other, of course. So that's one part. Moreover, we are going to show that the group of automorphisms of this field extension, assuming that E is an abelian finite Galois extension of field F with exponent n, then the Galois group of this extension is isomorphic to the group of all the group homomorphisms from delta of E to m sub n. This group is called the dual of delta of E. And we are going to show that this Galois group is isomorphic to the dual of delta of E. One can show that dual of abelian groups are isomorphic to the abelian groups. This can be done using classification of finite abelian groups and that we will discuss later. But as we will see, this isomorphism of delta of E and its dual is not a natural isomorphism. It's similar to the cyclic case that we discussed. So we can show that they are isomorphic in an existential way, but we cannot give a very nice concrete map from one to the other. But this map here is quite natural. We can actually give a natural isomorphism between the Galois group of E over F and the dual of delta V. Before we get to the proof of this result, I want to discuss a bit dual of abelian groups, understand them slightly better, and so on. And we will see how this understanding of dual of abelian groups, coupled with properties, important properties of Kumar pairing, can help us to finish the proof of these results. We have already seen the importance of Kumar pairing in the cyclic case, how we use the cyclic assumption to deduce that F sigma naught, F sub sigma naught, and F sub A naught bar, both of them are injective group homomorphisms, and those maps were crucial to show the Kummer theory for cyclic extensions. Now, here we need to know a bit more about abelian groups and the dual of abelian groups in order to be able to show this Kummer theory for the abelian case, finite abelian case of Kummer theory. Okay, so let's go and investigate dual of abelian groups. So suppose A is a finite abelian group. Dual of A is the set of all group homomorphisms from A to S bar. What is S bar? The set of all units length 1 complex numbers. So this is a circle of radius 1 centered at the origin. We know that if I give you Z1 and Z2, if both of them have norm 1, complex norm 1, then their product has complex norm 1, and therefore S1 is closed under multiplication. And here in this set, inverse of every element is the complex conjugate of that element, so it also belongs to S1. So it's a group under multiplication. And when I consider all the group homomorphisms from A to S1, the thing that we get, we call A bar. So it should also remind you of Fourier analysis if you know a bit about it. If you don't, that's fine. You don't need Fourier analysis for this part of the course. Now, knowing that, so if I tell you A has exponent n, then every element inside this group homomorphisms that I give you, chi, and every element inside the domain, chi of A to the n should be 1, because A to the n is 1. And a group homomorphism sends 1 to 1. But chi is a group homomorphism. That means chi of A raised to power n is 1. That means chi of A is an nth root of unity, which means chi of A belongs to M sub n. So there is this kind of ambiguity over here, because here I'm working with complex numbers, but there I'm working with F, and M sub n belongs to the nth roots of unity inside F. But you see the equation here. I could have I want to justify why there we are working with M sub n inside F cross, and it is kind of compatible with what we have over here. The point is that the groups that we are working over there are all of them have exponent n, and therefore I can identify the codomain with a subgroup of S1, and therefore what we have in the Kumar pairing and so on is compatible with the dual of finite abelian groups in this sense. So let's continue understanding the dual of abelian groups in this sense. So here in the statement, I claim that the group of automorphisms of E over F is isomorphic to the dual of delta of E. But I haven't told you what the group structure is for the dual. I have only told you about the set. So I need to introduce a multiplication on the dual of A. I give you two characters, so elements of elements of A bar, we call them characters. So I give you two characters of A bar. I give you two characters of A, chi1 and chi2. I need to define what is chi1 times chi2. It's supposed to be another character. This means when I need to apply it to an element inside A. It's supposed to be a function from A to S1. The way that we are going to define it is by pointwise multiplication. So we define it to be chi1 of A times chi2 of A. Remember, this is inside S1, this is inside S1. It does make sense to talk about their product. So I define it like this. Now I need to argue why this is an element inside a hat. This means, why is this a group homomorphism? So I feed it A1 times A2. I open it up, use the fact that chi1 is a group homomorphism, chi2 is a group homomorphism, reorder the terms and deduce that chi1 times chi2 is a group homomorphism. So altogether, we get that A hat and this multiplication is an abelian group, which is called the dual of A. Now, here is an extremely important lemma. If A is a finite abelian group of exponent n, if an element is non-trivial, we can detect it through characters. We can find an observer that doesn't kill A. So if A is a finite abelian group of exponent n, when I give you a non-trivial element of this group, there is an element of the dual that sends A not to 1, which does not contain A in its kernel. Okay, so let's see why this is the case. We will see the importance of this lemma later. Okay, so we notice that the abelian group is of exponent n. This means that order of every element divides n. Suppose order of A is n over m for some integer m. You see, it divides n, so it is definitely a fraction of n. Why did I choose it like this? Because I want to look at, you see, so let's make it a bit logical. I want to find this chi, where chi of A is not 1. If I was lucky and the group generated by this A was the entire group capital A, then how could I do it? So if A was already cyclic, then what? If A is cyclic, then I already know that I have 1 A squared, and I go till I go back. How many times should I go? Okay, that's exactly the order of A. The order of A, let's call it D for now. So I need to go D minus time once and D minus 1 times, and then I get back to 1. The reason that I put it on the circle is because I wanted to identify it with d roots of unity. So I can send A to the d root of unity, and that would be a group homomorphism from the cyclic group generated by A to M sub D. Now, M sub D is a subgroup of M sub n when D divides n, and it does because order of A divides n. Now, what is this generator if it was, if I want to think about dth root of unity as an element of nth roots of unity, I need to raise nth root of unity to power n over d in order to get the dth root of unity. That's why I denoted this guy by, instead of using d, I looked at n over m, so I call the power of the nth root of unity m. So that way I identify this with n over m. In any case, because a to the n is 1, order of A divides n, therefore it can be viewed as n over m. That's the same as this d that I have over here. Then I can define this character of the cyclic group generated by A to m sub n by sending A to power I to zeta to power m to power I. So maybe it's better to use j to not get confused with I in complex numbers. So this is going to be an abelian group homomorphism because this is a cyclic group. As soon as I assign an element to A, then if the order of what I'm assigning is compatible with order of A, which is the case here because the order of zeta to power m is n divided by m, it's compatible with this. So this means that this is in fact an isomorphism. So chi bar, not to this one, but it's an embedding. Chi bar is an embedding of the cyclic group. In particular, chi bar of A is not 1. So if the entire group was generated by small a, we were done. Now, what I want to do, I want to extend this chi bar to some character of A. If I manage to extend chi bar to a group homomorphism from A to S1, then we get a claim because then extension cannot send A to 1. So that's my goal. I want to extend chi bar to chi. I'm going to add one element after another. Alternatively, what am I going to do? I'm going to consider the set of all the pairs where the first component is a subgroup of A and the second component is a group homomorphism from this subgroup to S1. So this essentially belongs to the dual of H. So I'm looking at the pairs of H comma chi, where H is a subgroup of A, and this element A belongs to this subgroup. Moreover, when I restrict chi to this cyclic group generated by A, I get back chi bar. So this is a group homomorphism, and I have this property. So this is, sigma is such a set. And my claim is that this set has a maximal element, and the maximal element is definitely of the form A comma something, and then we are done. Okay, so again, the goal is to show that A comma something belongs to this set. If I show this, this is it, because then this means that I have managed to extend chi bar to some character of A, and that means that that character cannot send A to 1, and we would be done. As you can see, this is one of the largest possible, this is the largest possible element inside sigma. So I'm talking about largeness, so I need a kind of partial ordering on sigma. What is the partial ordering on sigma? I need to compare two elements of sigma. I need to say h1 comma chi1 is at most h2 comma chi2 if the first component is a subgroup of the first component, and second, chi2 restricted to the first subgroup is the same as chi1. So if I have such a phenomenon, then I say this pair is at most the other one. Now, because sigma is a finite set, with respect to any partial ordering, it has a maximal element. So sigma is a finite set because A is a finite abelian group. So this set, sigma, has a maximal element. Suppose h comma chi is such a maximal element. My claim is that h is A and we are done. We would be done if I show h is A. Suppose to the contrary that h is not A. So that means I can find some A prime inside A which is not inside H. I want to extend chi furthermore and include A prime in its domain. So this means I want to extend chi to the group generated by A prime and H. How does elements of the group generated by A prime and H look like? So elements of A prime and H, when I model by H, that's easy because that means I'm looking at the cyclic group generated by the coset A prime. So what I'm saying is that maybe I cannot completely understand the group generated by A prime and H immediately, but if I mod it out by the group H, and remember, these are all abelian groups, and therefore every subgroup is normal. So then this is the same as the group generated by A prime H. So this means that every element here looks like a power of A prime times H. Now, when I look at the pool back, this means every element in the group generated by A prime comma H is of the form A prime to power I times something inside H. So this gives us a fairly good understanding of the group generated by A prime and H. So I want to assign some value to A prime, but I need to be compatible with chi. So if some power of A prime is already inside H, I know what to assign to it. If it's not inside H, I might have a choice, but I have to make sure that my choice is compatible with what we have already assigned. In order to detect this, let's look at, again, this cyclic group that we have pointed out over here, the cyclic group generated by A prime and H. This cyclic group, let's say it has D naught or D elements. What does that mean? This means A prime raised to power D is inside H. Again, let's go slowly. If this cyclic group has D elements, that means the generator raised to power D is identity. That means A prime raised to power D should be inside H. Moreover, none of the smaller powers of A prime can be inside H. Because if they were, then A prime H raised to that power would have been identity of this quotient. So altogether, what I'm saying is, if D is the order of A prime H in the quotient, then A prime to power D is some element of H, and none of the smaller powers of A prime belong to H. Now, I want to assign something to A prime inside S1. But whatever it is, when I raise that guy to power D, it should be the same as what we have already assigned to h naught, because a prime raised to power d is h naught. Whatever we assign to a prime, when I raise it to power d, it should be the same as what we have assigned to h naught. So chi tilde, this is what we want to assign, chi tilde of a prime is a 0 of x to the d minus chi of h naught. Notice that chi of h naught itself raised to power n over d is a prime raised to power n, and that is 1. So this means that zeros of this binomial, all of them are nth roots of unity, so they do belong to n sub n, but there are only d of them, not all of them appear as a 0 of x to the d minus chi of h naught. We pick one of those zeros. We pick one of those zeros and assign it to a prime. So again, this argument that we have over here says that this chi of h naught raised to power n over d is 1. That means that every 0 of this polynomial does belong to set of nth roots of unity, or n sub n. Now, I want to extend this chi to the group generated by h and a prime. And as we have discussed over here, every element of the group generated by a prime and h is of the form a prime raised to some power times some element of h. Let me go over that argument again. The cyclic group generated by the coset a prime can be represented by a bunch of so it has finitely many cosets, precisely d, because we assume that d is the order of this coset. And the coset representatives can be chosen to be powers of a prime. So they are like this. And these cosets are distinct, and therefore they are disjoint. So this means that every element of the group generated by a prime and h, so the group generated by a prime and h modeled by h is this group, and therefore the numerator would be all the elements that can be inside the union of these cosets, the disjoint union, because they are distinct, therefore we get disjoint union of these sets. Now we define chi tilde from the group generated by a prime and h to n sub n. What is it? I need to tell you what a prime raised to power I times h is. And I set this guy to be chi tilde of a prime raised to power I, where chi tilde of a prime is a 0 of this binomial. Chi tilde of a prime raised to power I, and then for the h part, we know that we need to use chi. This is how we define chi tilde. Of course, I need to argue why it is well defined. Because here I am assuming that I can be anything inside this set of integers, so I can end up getting the same elements over here. And I need to argue why the right-hand side would be the same. So suppose a prime raised to power I1 times H1 is the same as a prime raised to power I2 times H2. Then why do I end up getting the same quantity on the left, on the right-hand side? What does this equality mean? This means a prime raised to power I1 minus I2 is inside H, and it is H2 times H1 times H1 times H2 H1 inverse. Okay, so that means that a prime, the coset represented by a prime in A over H, when I raise that coset to power I1 minus I2, I get 1, I get identity. Therefore, the order of that coset should divide I1 minus I2. The order of that coset is denoted by D. It's over here. So D should divide I1 minus I2, which means I1 minus I2 is D times I1 minus I2 divided by D. But remember, A to the A prime, okay, so where is it? A prime to the D, we denoted this guy by H naught, and it belongs to the group H. So A prime raised to power I1 minus I2, I can write it as A prime to power D to power I1 minus I2 over D. And A prime raised to power D is H naught. So I get that this is H naught raised to power I naught minus I2 divided by D. Remember, the exponent is indeed an integer, so it does make sense to talk about H naught raised to power that number. Therefore, when I apply chi to both sides, I get that chi of this, and we know that chi of this is, okay, so now I know that chi of this is, you see, A prime raised to power I1 minus I2 is H2 times H1 bar. Therefore, and that chi is H naught to power I1 minus I2 over D. So this means that chi of this is the same as chi of H2 times H1 inverse. Chi is a group homomorphism on H. So I get that chi of H2 times chi of H1 inverse is chi of H naught raised to power I1 minus I2 over D. But remember, chi tilde of A is chosen in this way, that chi tilde of A is 0 of this quantity. So chi tilde of A raised to power D chi tilde of A prime raised to power D is chi of H naught. Now, if I use this equality and raise both sides to power I1 minus I2 over D, what do I end up getting? This D cancels out this exponent, and I end up getting that this is the same as chi tilde of A prime raised to power I1 minus I2. That shows this product of these chi of H2 times chi of H1 inverse is the same as chi tilde of A prime raised to power I1 minus I2, which means that chi tilde of A prime raised to power I1 times chi of H1 is the same as chi tilde of A prime raised to power I2 times chi of H2. That's exactly saying that this is a well-defined function, because I chose these two different ways of writing the same element and then showed that the right-hand sides end up being the same elements. That means that chi tilde is well-defined. Now it's rather easy to check that chi tilde is a group homomorphism. The fact that chi tilde is an extension of chi is immediate, because I can just assign I to be 0 here, and I get that chi tilde of H is just chi of H. So it is immediate that it's an extension of chi. And the fact that it's a group homomorphism is rather easy. You feed it A to power I1 times A to power I2 times H1, H2. This is A raised to power this integer times this product of the elements belong to H. By definition, I need to apply chi tilde to A, raise it to power I1 plus I2, and let chi act on H1, H2. Now, when I want to show that this is a group homomorphism, I need to apply to this side, to each one of these elements separately. As I do so and use the definition, I get this element for the first factor and this element for the second factor. I can reorder the terms and end up getting the same product. So it's a group homomorphism, and the pair H comma chi is strictly smaller than the pair of the group generated by H and A prime and chi tilde, and that gives us a contradiction. And therefore, a maximal element of sigma looks like A comma chi for some chi. And that completes the proof of this lemma. Now let's see how this helps us. So we will continue on this in the next lecture. But let me summarize. We completed the proof of the Kummer theory for cyclic extensions, and we discussed what is dual of an abelian group in general, and why it is compatible what we have over here when we are working with abelian groups of exponent n. We defined dual, we showed that if A is a non-trivial element of a finite abelian group, then there is an element in the dual where chi of A is not 1. So we'll continue in the next lecture.